Here begins the journey for the soccer ball. Here is the gas nebula. The gas nebula is made up of cloud and dust. This is the protostar. It is the earliest phase of the life cycle of a star, which starts off as a gravity force in the gas nebula, sucking in clouds of gas and dust. This causes a nuclear reaction. If the temperature is over 100 million degrees, the star is born. Here is the main sequence star. This is the most stable part of a star's life. The core converts hydrogen into helium. The pressure from the nuclear reaction counteracts the force of gravity. To maintain the high pressure, the gas must be kept at a high temperature. Red giant star. For stars with a mass less than 8 solar masses, they transform into a red giant. After the star's core has completely converted from hydrogen to helium, the nuclear fusion ends. The star begins to contract gravitationally, causing the pressure and heat in the star to rise. The hydrogen in the inner layers then becomes hot enough to fuse into helium, and another nuclear fusion begins. This reaction adds heat to the star, causing the outer layers to expand. The star then cools and becomes a glowing red star. Variable star. The brightness of the star changes because the star is expanding. The nuclear fusion continues until all the helium in the core has been converted into carbon and oxygen. The nuclear fusion reaction ends and the core contracts under the force of gravity. The white dwarf and planetary nebula. For stars with a core less than 8 times the mass of the Sun, the temperature never becomes high enough to start the next nuclear fusion. The core contracts until the electrons can't be squeezed any closer together. It has the mass of the Sun but the size of Earth. As the star shrinks to a white dwarf, the outer layers form a ring of gas around the collapsing core known as a planetary nebula. Red supergiant star. For stars with a mass greater than 8 solar masses, the core is able to reach a higher temperature. In the outermost layers, hydrogen is being converted to helium. As we move to the core, helium is being converted to carbon and oxygen. Once iron is formed at the core, the run of nuclear reactions is complete. The atoms break up and neutrons are formed by the fusion of protons and electrons, causing a catastrophic collapse of the core. Supernova. When the core of a supergiant star has been transformed to neutrons, the collapse stops. This sends out a shockwave that blows off the outer layers of the star in a violent explosion. The energy released is greater than all the energy produced by the star over its entire lifetime. After the explosion, new elements are scattered into space, available for the formation of new stars. This explosion is known as a supernova. Pulsar or neutron star. After the supernova explosion, all that remains is the core of the star, completely made up of neutrons. A neutron star is as massive as our Sun, but only about 20 kilometers in diameter. A special type of neutron star is the pulsar. Pulsars give off radio beams at their magnetic poles. The pulsar spins like a lighthouse, and the radio beams pass by the Earth, producing pulses of radio noise. All that is left of the star after the outer layers are ejected to space is the core remnant. The core's gas is super compressed by gravity to form a strange type of gas made of degenerate matter. It is important to remember what happens to the core depends on the mass of the core, rather than the original mass of the main sequence star from which it came, because the only thing left of gravity to really compress is the core. Black hole. If the stellar core is greater than 3 times the mass of the Sun, the catastrophic collapse which produced the neutron star continues until the core becomes extremely dense and incredibly small. The gravitational pull becomes so great that not even light can escape it. A black hole is formed.